Hello, Chem 212 students, and welcome back for our next set of lectures where we continue on Chapter 22, Amines. When we left last time, we had discussed various methods of creating amines, including primary amines and also secondary and tertiary amines. For the creation of primary amines, we had three primary pathways. The Gabriel synthesis, starting with the usage of a phthalimide ion, potassium phthalimide here, and reaction with an alkyl halide following up by H2NNH2 there. And that would give us the primary amine, or the use of sodium azide as a reagent, again reacting with a primary amine, followed by a reduction with hydrogen and platinum to give us the final amine. Also, there was reductive amination, the reaction of ammonia with a aldehyde and followed up with reducing agent cyanoborohydride to produce the primary amine. For secondary and tertiary amines, the creation of these amines involved the reductive amination of a primary amine to a secondary amine, tertiary amine, and finally the last alkylation here would produce for us a quaternary ammonium ion. In this following chapter, in the following slides, we're going to now discuss the reactions of amines, some of which we've seen before and some of which will be new. So the first reaction that we will discuss will be one that we have seen before. These are the reactions of amines with an acyl chloride. And so the acyl here meaning the chloride here being attached to the carbon that's involved in a carbonyl carbon-oxygen double bond here. And in this case, 2 moles of the amine will be required. And in addition, the acylation of the amine can be used as a protecting group for a variety of other reactions. Ultimately, the nitrogen here ends up attached to the carbon atom. Of course, we can see that one hydrogen here is lost. That's going to be removed by the second mole of amine here, the second stoichiometric quantity, which is going to be used to deprotonate the resulting product. And so the mechanism, just recall, involves here the attack of the amine on the oxygen and the resonance arrow here, then creating for us this this complex here where we have the nitrogen here that is attached to this carbon. This oxygen is now it had 2 lone pairs to start. Now it has 3, so 3 lone pairs and 1 bond, giving it a -1 formal charge. The nitrogen here in this case has a alkyl group attached and 2 hydrogens, and now it has 4 bonds and no lone pairs, giving it a positive formal charge. This is going to be followed by a step in which the chloride is expelled as a leaving group here. And that's going to leave us with this. I'll draw in red again. That's going to leave us now with this oxygen, now again making a double bond, giving it 2 bonds and no lone pairs, and thus 0 formal charge. And then we have the nitrogen with still 1 alkyl group and 2 hydrogens, again 4 bonds and no lone pairs, giving it a positive formal charge. And this is where the second equivalent of the amine is valuable. This is going to be used then to finally deprotonate the resulting ammonium salt here and give us the neutral product here. Ultimately, this leads us to our result here, right here. And so this is an old mechanism from previous the chapter 19 ketone and aldehydes chapter. And so that's just a kind of revisiting here this mechanism. But so we can make for ourselves an amide by reacting an amine with an acyl chloride. So another type of reaction that we can use with amines is with the aniline here. If we react aniline with bromine, remember that aniline is an orthopero activator here, and so when we react with bromine, it can undergo an electrophilic aromatic substitution, like we saw in chapter 20, I believe it was. And so this electrophilic aromatic substitution, remember electrophilic here, the bromine being the electrophile. Of course, we generally use like things like AlBr3 and instead, but equivalently here we can have just very simply, we saw this kind of version of the mechanism, this alternative version where we have the nucleophilic attack on the bromine here, thus giving us the bromine attached here at the ends up being attached here at this position. And this can happen 3 times. We can get this bromination. There's another step where you finally take the second proton off and get your double bond back. But this is just a revisiting of prior mechanisms as well. Here, though, the amino group is a very powerful activating group, and so that's why we end up usually getting polybrominations at all of the ortho and para positions unless there are other groups directing that. So one way of avoiding that is to make a less powerful activating group. And so this was what we would consider a strong activator. By using the same reaction we saw before, we can turn this strong activator into an only moderate activator, which will help us to control the reaction better and stop it before we get this polyhalogenation. And so we then react this amine with an acyl chloride as we saw before, and by the same mechanism we get an amide. And so when we get this amide and we treat it with bromine, now it's going to be only a moderate activator, and the reason why is because this oxygen here does pull some electron density away from the ring, right? A little bit. I mean, it's not completely. It's still an activator. It's going to provide electron density to the ring, allowing it to be the nucleophile and provide electrons to the electrophile. However, it's not so strong of an activator that you get uncontrollable polyhalogenation here. You can then halogenate at the para position here where we have this bromine, and then you can then undo this this conversion into an amide by treating with sodium hydroxide or a base. So this will be acid or base catalyzed hydrolysis of this, and then we can ultimately get our amine back here, and then we can monobrominate at the para position. Now, for this this aniline here, anilines cannot undergo a Friedel-Crafts acylation or alkylation directly. And the reason why is that the aluminum chloride here will behave as the electrophile, yes, like we would expect, but it's not going to be reacting with the benzene ring this time. More nucleophilic here will be the lone pair on the nitrogen, as we saw before when that attacked the acyl chloride. This nucleophilic lone pair here will go and attack this electrophilic aluminum, the aluminum behaving as a Lewis acid and accepting those electrons, and the nitrogen here being the Lewis base and donating them. And so at this point, this nitrogen will have 4 bonds, or 2 to the hydrogen, 1 to the carbon, and 1 to the aluminum. So with 4 bonds and no lone pairs, that gives the nitrogen a positive 1 formal charge. For the aluminum, we don't have our shortcuts that we would normally have, but we can see that it has 4 bonds. So if we use the normal formal charge accounting method, we'd say is aluminum is in group 3 of the periodic table. It starts with 3 valence electrons. However, if we split each bond in half and give one of those electrons to aluminum, like we do when we're counting formal charge, it has 4 dots in its little circle here, which is 1 extra electron compared to its normal 3, giving it a -1 formal charge. And at that point, this is strongly deactivating to the ring. You have this positive formal charge on the nitrogen. We are pulling electron density from the ring, which means that it will no longer participate in this Friedel-Crafts acylation. And so this is another way here that we can deal with that here, is that if we want to do a Friedel-Crafts acylation, we can begin by converting this nucleophilic nitrogen into a nitrogen that's not nucleophilic. So the first step is the same here. Again, we have this nucleophilic attack of the nitrogen on the carbonyl, and we have a few more steps that I showed you in the mechanism before, but ultimately that leads us to an amide. Now in this amide, the electron density on the nitrogen lone pair here is spread out significantly more, because not only is it resonant with the ring, but it also has further resonance here with this carbonyl group. And so this really spreads out the electron density, making the nitrogen significantly less nucleophilic. And so that means that now the benzene ring can behave as a nucleophile. And you guys hopefully will recall the Friedel-Crafts alkylation and acylation when we have the combination here of an alkyl chloride with the AlCl3, the trichloroaluminum here. We're going to have a chlorine that then is attached to the aluminum here, and it produces this complex where the aluminum now has a negative formal charge here, and the positive here, the chlorine here has a positive formal charge, making it an attractive electrophile. And when this Friedel-Crafts reaction completes, we end up with the alkylation at the para position. Again, the amides here, they're moderately activating to the ring, ortho para directing. However, we'll just primarily get the ortho product due to the steric hindrance here, or the para product here rather, due to the steric hindrance at the ortho positions. We can then treat with, we can then hydrolyze the amide with treatment with sodium hydroxide or any acid here, and then ultimately recover our amine. And so although amines cannot participate in Friedel-Crafts acylation or alkylation, they can be protected in this way, and then subsequently participate and then be hydrolyzed again to return to the amine. Now, like alcohols, amines can serve as precursors for the synthesis of alkenes. We can do an elimination of these to produce an alkene, so we just treat with generally treat with some kind of a base here. Elimination, treat with a base, right? And that base, let's say with this base here, negative, if we have a hydrogen here, we can have a E2 reaction here where we have a deprotonation followed by these two electrons here in this bond becoming the pi bond, and the simultaneous leaving of the amine leaving group in an E2 reaction, and ultimately produce for us our alkene. Similarly, this can be done with alcohols. So we can produce alkenes from amines by treatment with a base. Now, one issue here is that this is a terrible leaving group. So this would actually not occur as we see here. So similarly, hydroxide is a terrible leaving group. So what do? Well, we'll either do this in an acidic. We can do an elimination by treatment with acid, which would protonate the hydroxyl group. Or a lot of times what we do for the alcohol is we'll treat with tosyl chloride and pyridine, and then we'll turn this into a tosylate, and then we'll treat with the base, and the tosylate is a great leaving group. So we have an alternative mechanism we can use to make the amine into a good leaving group. We can alkylate it. And so if you may recall previously here, we can alkylate the amine in an SN2 style reaction here, where this lone pair attacks the electrophilic carbon and the iodide leaves, and that adds for us an alkyl group here. We can continue to add more and more alkyl groups until we got a quaternary ammonium ion. quaternary ammonium salt. And this quaternary ammonium salt means that this nitrogen here will be a good leaving group. It will leave as a neutral amine. And so what we do is we treat with excess an excess alkyl iodide here, and then we'd use a strong base to do an E2 elimination. However, commonly, practically speaking, silver oxide is used, and silver oxide here is used in the same way as a base would be used to ultimately produce the alkene. Now, there's something you may notice about this alkene is that it is the less substituted alkene. So the question is, how come we did not get the more substituted alkene out of this reaction? Which it would be a very good question, because generally we're going to get the more substituted amine. But recall, like this, recall that this must proceed through an E2 reaction mechanism. So when it's proceeding through an E2 reaction mechanism, our hydrogens must be positioned anti-periplanar to the leaving group here, and the leaving group being the amine group that gets alkylated like this. So this is the leaving group here. Well, over here we've got 2 hydrogen atoms, and over here we have 3. So on the end here, doing an elimination where it turns out that doing the elimination over here where we can and this would be, of course, this would be the ammonia, not this group itself, but really this group we're talking about. It has to be a good leaving group. But generally speaking, I mean, you can really eliminate from any position here. You have 3 different hydrogens, but the same cannot be said for the left side. And so we're going to need this amine here to be or this what's going to be the quaternary ammonium salt here to be with this group in a position that is anti-periplanar to these hydrogens, which it turns out is not so simple a matter, because that ends up putting this very bulky group next to another bulky group, which is going to have steric hindrance, and so those will have a very high energetic barrier to getting into that configuration. So here, when we have, as I said, when we have the quaternary ammonium salt that we produce from the amine by reacting with excess methyl iodide, we can then have a strong base come in and pull a proton from the carbon here at the end, and this is the normal E2 mechanism, deprotonated on the carbon right next to the leaving group here. The electrons that were involved in the bond between the hydrogen and the carbon are now moved into a pi bond here at this position, and then finally we have the loss of a neutral amine here. So a neutral amine, meaning that this was a good leaving group, and we also get the formation of water as a result of the hydroxide grabbing the proton. So Hoffman eliminations are going to give the terminal alkene, the less substituted alkene, selectively. This is something that almost must be memorized in a sense, because although you can work it out, it takes a long time. You want to maybe have worked it out once to demonstrate it to yourself, then just try to keep it in mind that this bulky group is not going to want to be positioned in a way that puts it close to this other bulky group. We can see that if we use a Newman projection. So it's been a while since you guys might have seen a Newman projection. So I'll just remind you that the way it works is we draw it from the perspective of looking down a bond between 2 carbons. In this case, we're going to be looking down the carbon 2 to carbon 3 bond. Now, if we're looking down this bond, we're going to, this line here must be either a wedge or it must be a dash. Now, given that I'm looking here from right to left, if it is a wedge, it will be on my left, and if it is on a dash, it will be on my right. And so if I'm looking this way, right, and this is looking down the page, like that eyeball is, the left is in front of the page, and the right is on the back of the page. So the way that it's written here on this Newman projection is that the methyl is on the right, meaning the back of the page. So another way that I could draw this here, we're assuming that this is in the plane, is to put this on a wedge, and then the hydrogen here would be on the dash. And so that's the way we can see it right here. Now on the back side here, if we put this group right here, we're going to say, okay, if we want a hydrogen to be anti-periplanar to this, we're going to have one hydrogen that is in the plane of the page. Okay, so this one in the plane of the page, I'm going to draw it right here, making this hydrogen that's in the plane of the page. Now, as I said, we're looking from right to left here, so a dash will be on the right side of our Newman projection. A wedge, which pops out of the page, will be on the left side, right? Imagine you're turned this way. I'm turned this way. I'm looking down the page. Then the wedges are on. The wedges here are on the left side, and the dashes are on the right side, right? So actually, I think I got this reversed here. So the wedge will be the hydrogen. The dash will be the methyl. So let's break this down here. So we're looking left to right here. Our dashes are on the right side. So this is our dash right side. And this is our wedge left side. Okay. So this is my dash here. This is the dash, which is the methyl group. So that's why we put the methyl group right over here. It's the dash to the right. My wedge, the hydrogen, is on the left. Okay. And so over here now, I'm going to have this guy, which will be on a dash, and the wedge, again, will be on the, this group here will be on the wedge, and the hydrogen will be on the dash here. And this hydrogen is in the plane of the page. So what we have here is we have the 1, 2, 3, this propyl group here. This is on the wedge, on the dash left. So the wedge left rather, and the hydrogen is on the dash right. And so we can see the hydrogen here on the dash right, and the propyl group here on the wedge left. And what this results in is a gauche interaction here. And so rotating into this position is not going to be a very comfortable position for this molecule here. Now, likewise, if we look down the C2 to C1 bond, now this time we're looking from right to left here, and so any kind of now that we're looking, or from left to right, now that we're looking like this way down the page. So whatever is behind the page is going to be on our left. So it's going to be dash left. And whatever's in front of the page, if we're looking, down this way on the page, what's popping out of the page is going to be on our right. Wedge. Right. And when you look at it this way, really there's 3 hydrogens now on this back carbon. So it doesn't really matter. As long as we have this group here positioned in a way that's far away from this group, we can pull this hydrogen very easily. So for the first situation, there's no way to do that without having this gauche interaction. So it's very, very difficult. It's going to be high in energy to get to this position so that we can eliminate and produce this more substituted double bond. But here we can easily, any of these hydrogens in the back, there's 3 of them because there's 3 hydrogens on this first carbon here. Any of these hydrogens on the back can be used. But the molecule is going to most likely be in the position where this propyl group is far away and not in a gauche interaction with this cation here. And so ultimately, when we get our elimination, it's going to be a lot easier to get the less substituted elimination, even though the more substituted alkene is more thermodynamically stable. Kinetically, there's a huge barrier because of the energy barrier of achieving the transition state. But here, there's not an energy barrier of rotating into this position, not a significant energy barrier like this one. And so there's going to be very little kinetic barrier to producing this less substituted alkene. So even though it's less thermodynamically stable, it will be produced at a much faster rate. And so that is the reason why this reaction here will produce a less substituted alkene rather than a more substituted alkene. And this is referred to as the Hoffman elimination. And recall we had the Zaitsev versus the Hoffman product, right? When we used to, going back here, we used to call this the Zaitsev product of elimination, and we would call this the Hoffman product. And this is it's the same guy we're talking about here. Product. So that's going to be the end of this video. In the next video, we're going to finish the amine chapter by talking about a few more reactions of amines, and finally the considerations when reading mass spectra, IR spectra, and NMR spectra that contain amines. I'll see you in the next video.